centuries, the speed of light has been regarded as the ultimate constant, the very foundation of our understanding of time, space, and the universe. Scientists have measured it at exactly 299,792,458 meters per second. This number has become sacred in physics, appearing in Einstein's famous equation E equals mc squared, where c represents the speed of light. It governs how fast information can travel, how quickly spacecraft can journey between worlds, and even how time itself flows throughout the cosmos. But what if this constant is not constant after all? What if the speed of light is slowing down, changing as the universe evolves over billions of years? Tonight, we explore a possibility that challenges everything we thought we knew about reality itself. We venture into a realm where the most fundamental law of physics might be more flexible than we ever imagined. Imagine standing beneath a starlit sky, watching light that has traveled for millions of years to reach your eyes. That ancient starlight carries secrets from the distant past, potentially holding evidence that the very speed at which it traveled has been gradually decreasing throughout cosmic history. If true, this discovery would revolutionize our understanding of space, time, and the nature of existence itself. The implications stretch far beyond academic curiosity. A changing speed of light could mean that our measurements of the universe's age are wrong, that distant galaxies are not where we think they are, and that time itself behaves differently than we have assumed. It could reshape our understanding of black holes, the Big Bang, and the ultimate fate of everything we see around us. Consider the profound questions this raises. If light is slowing down, what does this mean for the fundamental forces that hold atoms together? How would this affect the delicate balance that allows stars to shine and planets to orbit? Could this change explain some of the mysterious phenomena that astronomers observe in the deepest reaches of space? As we embark on this journey together, we will examine the evidence, explore the theories, and contemplate what it would mean if one of our most cherished scientific constants is actually variable. We will travel through time and space, from the laboratories where scientists first measured light's speed to the distant quasars whose ancient light might hold the key to understanding whether our universe operates under rules that are slowly, imperceptibly changing. What we discover tonight might challenge your deepest assumptions about reality. The speed of light has been our cosmic speed limit, our universal reference point, our unwavering constant in an ever-changing universe. But what if this foundation is shifting beneath our feet? What if the speed of light is not the immutable constant we believed it to be, but rather a slowly evolving property of space-time itself? The story we are about to tell is one of scientific detective work, of researchers following clues scattered across billions of light years and billions of years of cosmic history. It is a tale of how the most careful measurements and the most sophisticated theories might need to be reconsidered in light of new evidence. Tonight, we explore the fascinating possibility that what we know about the speed of light might be just the beginning of a much larger, more mysterious story. In the early 1900s, a young patent clerk named Albert Einstein proposed something extraordinary. He suggested that the speed of light in a vacuum is the same for all observers, regardless of how fast they are moving. This simple idea became the cornerstone of his special theory of relativity, forever changing how we understand space and time. The number itself is breathtaking in its precision. Light travels at exactly 299,792,458 meters per second in empty space. To put this in perspective, light could circle the Earth more than 7 times in just 1 second. It could travel from the Earth to the Moon in about 1 1/3 seconds. This incredible speed represents the ultimate speed limit of the universe, the fastest that any information or energy can travel through space. Einstein's breakthrough revealed that space and time are not separate entities, but are woven together into a single fabric called space-time. The speed of light is the thread that binds this fabric together. When objects approach the speed of light, time begins to slow down relative to stationary observers. Space itself contracts in the direction of motion. These effects, once considered impossible, have been confirmed countless times through experiments and observations. Modern physics depends entirely on the constancy of light speed. Our understanding of energy and mass, expressed in Einstein's famous equation E equals mc squared, relies on c being unchanging. Here, c represents the speed of light, and its square appears as the conversion factor between mass and energy. This relationship explains how the sun produces energy, how nuclear reactors work, and even how tiny amounts of matter can release enormous amounts of energy. The speed of light also determines the structure of atoms themselves. Electrons orbit atomic nuclei at speeds related to the speed of light through something called the fine structure constant. This dimensionless number, approximately equal to 1 divided by 137, describes the strength of electromagnetic interactions. It governs how tightly electrons are bound to their nuclei and influences the colors of light that atoms can absorb and emit. In the realm of cosmology, the speed of light serves as our cosmic ruler. Astronomers measure distances to far-off galaxies by observing how their light has been stretched by the expansion of the universe. They calculate the age of the universe by determining how long light has been traveling from the most distant observable objects. The cosmic microwave background radiation, the afterglow of the Big Bang itself, provides a snapshot of the universe when it was only 380,000 years old, based on calculations involving the speed of light. Particle physicists use the speed of light to understand the fundamental forces of nature. The electromagnetic force, which governs how charged particles interact, is mediated by photons that always travel at the speed of light. The weak nuclear force, responsible for certain types of radioactive decay, is also intimately connected to light speed through the unified electroweak theory. Even gravity, according to Einstein's general theory of relativity, propagates at the speed of light through ripples in space-time called gravitational waves. Our modern technology depends on the constancy of light speed in countless ways. Global positioning satellites must account for relativistic effects caused by their high speeds and different gravitational environments. Fiber optic communications rely on light pulses, traveling at predictable speeds through glass cables. Particle accelerators push subatomic particles to near light speed, and their precise operation depends on knowing exactly how fast light travels. The speed of light also defines the boundaries of our observable universe. We can only see objects whose light has had time to reach us since the universe began. This creates what astronomers call the cosmic light horizon, beyond which we cannot observe because there has not been enough time for light to travel from those distant regions to Earth. But what if this fundamental constant, this cosmic speed limit that governs everything from atomic structure to the expansion of the universe, is not actually constant? What if the speed of light has been slowly changing throughout cosmic history, so gradually that we have only recently begun to detect its subtle variations? The implications would be staggering, requiring us to reconsider everything we think we know about the nature of reality itself. The speed of light is the very measure of time and distance in our universe. It connects the smallest scales of quantum mechanics to the largest scales of cosmology. It determines how fast information can travel, how quickly cause can lead to effect, and even what events can be considered simultaneous. But what if this measure changes over time? What if the ruler we use to measure the cosmos is itself slowly shrinking? To truly appreciate the significance of light speed, we must understand how deeply it permeates every aspect of physical reality. In quantum mechanics, the speed of light appears in the uncertainty principle, which states that we cannot simultaneously know both the exact position and momentum of a particle. This fundamental limit on knowledge itself depends on the speed of light through Planck's constant and other fundamental quantities. The electromagnetic spectrum, from radio waves to gamma rays, all travels at this same speed through empty space. Radio telescopes detect signals from pulsars, rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. These signals arrive at Earth with timing so precise that astronomers use them as natural atomic clocks scattered throughout the galaxy. The consistency of these arrival times over decades of observation provides one of our most stringent tests of whether the speed of light has remained constant. In the world of high-energy physics, particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.99999% of the speed of light. At these extreme velocities, the particle's behavior becomes dominated by relativistic effects. Their mass increases dramatically as they approach light speed, requiring ever more energy to accelerate them further. This energy requirement grows without bound as the particles approach the speed of light. making it impossible for any massive object to actually reach this cosmic speed limit. The speed of light also governs the behavior of black holes, those mysterious objects where gravity becomes so strong that not even light can escape. The boundary around a black hole, called the event horizon, is defined as the distance from the center, where the escape velocity equals the speed of light. Inside this boundary, space and time become so distorted that conventional physics breaks down. The information paradox, one of the deepest puzzles in modern physics, arises from the conflict between quantum mechanics and general relativity, at these extreme conditions where light speed plays a crucial role. Stellar astronomy relies heavily on the constancy of light speed. When we observe a supernova explosion in a distant galaxy, we see the light from this catastrophic event arrive at different times depending on the wavelength. This phenomenon, called dispersion, occurs because the light passes through clouds of interstellar gas and dust on its journey to Earth. By analyzing how different colors of light arrive at slightly different times, astronomers can probe the properties of the material between stars and test whether the speed of light is truly the same for all wavelengths. The cosmic microwave background radiation, discovered in 1965, provides another crucial test of light speed constancy. This radiation has been traveling through space for over 13 billion years, since the universe cooled enough for atoms to form and space became transparent to light. The remarkable uniformity of this radiation across the entire sky suggests that the speed of light has remained constant over cosmic timescales. Any variation in light speed would have left detectable imprints in the temperature fluctuations we observe today. Modern cosmology depends on the assumption that fundamental constants, including the speed of light, have remained unchanged since the Big Bang. The theory of cosmic inflation, which explains why the universe appears so uniform on large scales, requires the speed of light to have been constant during the first fraction of a second after the universe began. If light speed were changing, the mathematical models that describe inflation would need to be completely revised. The search for extraterrestrial intelligence also relies on the constancy of light speed. Radio telescopes scan the skies for artificial signals that might indicate the presence of technological civilizations around other stars. The protocols for interpreting such signals assume that the fundamental constants of physics, including the speed of light, are the same throughout the galaxy. A civilization trying to communicate across interstellar distances would naturally use these constants as reference points for their messages. Quantum field theory, the mathematical framework that describes the behavior of subatomic particles, treats the speed of light as a fundamental parameter that defines the structure of spacetime itself. The theory predicts the existence of virtual particles that constantly pop in and out of existence in empty space. These quantum fluctuations contribute to the energy density of the vacuum and influence the behavior of real particles. The calculations that predict these effects depend critically on the assumed constancy of the speed of light. Even the definition of basic units in physics depends on light speed. The meter, the fundamental unit of length, is now defined as the distance light travels in 1,299,792,458 of a second. This definition assumes that the speed of light is exactly 299,792,458 meters per second by definition. If the speed of light were changing, we would need to reconsider how we define distance itself. The Global Positioning System provides a practical example of how light speed constancy affects daily life. GPS satellites orbit Earth at speeds of about 14,000 kilometers per hour and experience gravitational fields different from those at Earth's surface. These conditions cause the satellite clocks to run at slightly different rates than clocks on the ground, an effect predicted by Einstein's theories of relativity. The GPS system must continuously correct for these time differences to maintain its accuracy. If the speed of light were changing, these corrections would gradually become less accurate, and the system would slowly drift out of alignment. The speed of light is the very measure of time and distance. It connects the smallest scales of quantum mechanics to the largest scales of cosmology. It determines how fast information can travel, how quickly cause can lead to effect, and even what events can be considered simultaneous. But what if this measure changes over time? The quest to measure the speed of light began with humanity's earliest attempts to understand the nature of vision itself. Ancient Greek philosophers debated whether light traveled from our eyes to illuminate objects, or whether objects somehow sent light to our eyes. Empedocles, around 450 BC, proposed that light must travel at finite speed, though he had no way to measure it. Aristotle disagreed, arguing that light traveled instantaneously, a belief that would persist for nearly 2,000 years. The first serious attempt to measure light speed came from Galileo Galilei in the early 1600s. He stationed himself on one hilltop and an assistant on another, each holding a lantern. Galileo would uncover his lantern, and his assistant would uncover his own lantern as soon as he saw Galileo's light. By timing the delay between uncovering his lantern and seeing his assistant's response, Galileo hoped to measure how long light took to travel between the hills. Unfortunately, human reaction time was far too slow to detect light's incredible speed over such short distances, and Galileo concluded only that light traveled very fast, possibly instantaneously. The breakthrough came from an unexpected source. In 1676, Danish astronomer Ole Rømer was studying the moons of Jupiter, particularly Io, which orbits the giant planet every 42.5 hours. Rømer noticed something peculiar. When Earth was moving toward Jupiter in its orbit, Io's eclipses occurred slightly earlier than predicted. When Earth was moving away from Jupiter, the eclipses happened slightly later. Rømer realized that this timing difference occurred because light from Jupiter's system took longer to reach Earth when the planets were farther apart. By carefully measuring these timing variations over many months, Rømer calculated that light took about 22 minutes to cross Earth's orbital diameter. This gave him a speed of light of approximately 214,000 kilometers per second, remarkably close to the true value, considering the limited precision of 17th century measurements. For the first time in human history, someone had demonstrated that light travels at finite speed and had provided a reasonable estimate of that speed. James Bradley, an English astronomer, provided the next major advance in 1728 through his discovery of stellar aberration. As Earth orbits the Sun, nearby stars appear to trace tiny ellipses in the sky, not because the stars are actually moving, but because of Earth's motion combined with light's finite speed. This effect is similar to how raindrops appear to come at an angle when you're walking through a rainstorm, even if the rain is falling straight down. Bradley's precise measurements of stellar aberration provided another confirmation that light travels at finite speed and allowed him to calculate a value very close to modern measurements. The 1800s brought increasingly sophisticated attempts to measure light speed directly on Earth. French physicist Hippolyte Fizeau designed an ingenious experiment in 1849 using a rapidly spinning toothed wheel. He aimed a beam of light through the gaps between teeth, reflected it off a mirror several kilometers away, and observed the returning light. By spinning the wheel at different speeds, he could determine exactly how fast it needed to rotate for the returning light to be blocked by a tooth rather than passing through a gap. This gave him the time light took to make the round trip, and thus its speed. Léon Foucault improved on Fizeau's method in 1850, replacing the toothed wheel with a rapidly rotating mirror. As light traveled to a distant reflector and back, the rotating mirror would turn slightly, deflecting the returning beam by a measurable angle. Foucault's measurements were more precise than Fizeau's and confirmed that light travels slower in water than in air, supporting the wave theory of light over the particle theory that had been popular at the time. The most famous and precise measurements came from Albert Michelson, beginning in 1878. Michelson dedicated much of his career to perfecting the measurement of light speed, developing increasingly sophisticated rotating mirror systems. His work culminated in measurements accurate to within a few parts per million, establishing the speed of light as 299,796,000 kilometers per second, very close to today's accepted value. Michelson's obsession with measuring light speed led him to collaborate with Edward Morley on what became known as the Michelson-Morley experiment in 1887. They expected to detect Earth's motion through the hypothetical luminiferous ether, the medium that 19th century physicists believed must carry light waves. Their interferometer split a light beam, sent the two parts along perpendicular paths, then recombined them to look for interference patterns that would reveal Earth's motion through the ether. The result was one of the most important null results in the history of science. No matter how they oriented their apparatus or when they performed the experiment, Michelson and Morley found no evidence of Earth's motion through the ether. Light appeared to travel at the same speed in all directions, regardless of Earth's motion. This puzzling result troubled physicists for nearly 2 decades, until Einstein provided the explanation through his special theory of relativity. Einstein's 1905 paper on special relativity began with 2 simple postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate directly addressed the mystery of the Michelson-Morley experiment. There was no ether because none was needed. Light does not require a medium, and its speed is truly constant for all observers. The implications were revolutionary. If light speed is constant for all observers, then space and time must be relative. Moving clocks run slow, moving rulers contract, and simultaneity depends on the observer's reference frame. These effects, collectively known as time dilation and length contraction, have been confirmed in countless experiments, using everything from fast-moving particles to precision atomic clocks flown on aircraft. Throughout the 20th century, improvements in technology allowed ever more precise measurements of light speed. Laser interferometry, atomic clocks, and electronic timing systems pushed the precision to extraordinary levels. By 1972, measurements were accurate to within 4 parts in 10 to the 9th power. The precision became so great that uncertainties in the definition of the meter, rather than measurement errors, became the limiting factor. This situation led to a fundamental change in how we define basic units. In 1983, the International Committee for Weights and Measures redefined the meter in terms of the speed of light. Instead of trying to measure light speed more precisely, they declared its speed to be exactly 299,792,458 meters per second by definition. The meter became the distance light travels in that precise fraction of a second. Modern tests of light speed constancy have become incredibly sophisticated. Laser ranging experiments bounce light off reflectors placed on the moon by Apollo astronauts, measuring the round-trip time with nanosecond precision. These measurements, conducted over decades, show no detectable change in light speed. Similarly, pulsar timing arrays monitor the arrival times of radio pulses from rapidly spinning neutron stars scattered throughout our galaxy, providing another test of whether light speed remains constant over time and distance. Laboratory tests using atomic clocks have reached extraordinary precision. These experiments compare the frequencies of different atomic transitions, looking for any drift that might indicate changing fundamental constants. Some experiments monitor single-trapped ions for months, measuring their internal quantum states with precision that approaches the fundamental limits imposed by quantum mechanics itself. The constancy of light speed has become so well established that it serves as the foundation for our most precise measurements of space and time. Laser interferometer gravitational wave observatories like LIGO rely on the assumption that light speed is constant to detect tiny distortions in spacetime caused by colliding black holes and neutron stars, billions of light years away. Global positioning satellites depend on this constancy for the precision timing that enables accurate navigation. Yet even as we celebrate these technological achievements built on the foundation of constant light speed, a nagging question remains. All of our measurements span relatively short time periods compared to the age of the universe. We have confirmed light speed constancy over decades, centuries at most. But what about over millions, billions, or tens of billions of years? Could the speed of light be slowly changing on timescales too long for human civilization to detect directly? For over a century, we have known the speed of light as a constant, the unchanging foundation upon which the edifice of modern physics rests. But could this belief be challenged by new evidence from the deepest reaches of space and time? The first hints that the speed of light might not be constant came from an unexpected source: careful analysis of ancient astronomical records. In the 1990s, researchers began examining centuries-old observations of eclipses, planetary positions, and stellar events, comparing them with modern calculations. What they found was puzzling. Some ancient observations seemed slightly inconsistent with what we would expect if physical constants had remained unchanged throughout history. Chinese astronomers had been meticulously recording solar eclipses for over 2,000 years. When modern scientists used computer models to calculate when these eclipses should have occurred, assuming constant physical laws, they found small but persistent discrepancies. The ancient observations suggested that Earth's rotation had been slowing down more rapidly than could be explained by tidal friction alone. Could changing fundamental constants, including the speed of light, account for these mysterious differences? Similar puzzles emerged from studies of ancient Babylonian astronomical tablets. These clay records, dating back over 2.5 millennia, contain precise observations of lunar eclipses and planetary motions. When researchers attempted to match these observations with modern orbital calculations, they discovered systematic errors that seemed to grow larger the further back in time they looked. The discrepancies were small, just fractions of degrees in celestial positions, but they were consistent and troubling. The modern search for evidence of changing light speed began in earnest when astronomers realized they possessed a unique laboratory, the distant universe itself. Light from faraway galaxies has been traveling for billions of years to reach us. If the speed of light has been changing over cosmic time, this ancient light might carry evidence of those changes encoded in its spectrum, intensity, and arrival time. One of the most promising approaches involves studying quasars, the brilliant cores of distant galaxies powered by supermassive black holes. These objects are so luminous that we can observe them across most of the visible universe, seeing them as they existed when the cosmos was much younger. Quasars emit light at many different wavelengths, and this light passes through intervening clouds of gas on its journey to Earth. As quasar light travels through these gas clouds, atoms absorb photons at very specific wavelengths, creating dark absorption lines in the spectrum. The positions of these absorption lines depend on fundamental constants, including the fine structure constant, which is directly related to the speed of light. By comparing the wavelengths of absorption lines from distant quasars with the same transitions measured in laboratory experiments, astronomers can test whether fundamental constants have remained unchanged over billions of years. In 1999, a team led by John Webb at the University of New South Wales announced startling results from their analysis of quasar spectra. They had studied light from distant quasars that had been traveling for up to 12 billion years, and they found systematic shifts in the absorption line wavelengths that suggested the fine structure constant had been smaller in the past. If confirmed, this would imply that the speed of light had been larger when the universe was young and has been gradually decreasing over cosmic time. The Webb team's measurements suggested that the fine structure constant had increased by about 6 parts per million over the past 12 billion years. This might seem like a tiny change, but its implications would be enormous. A varying fine structure constant means that either the speed of light is changing, or the elementary electric charge is changing, or both. Given the central role of light speed in relativity theory, many physicists found the possibility of a changing speed of light easier to accept than a changing electric charge. However, the results proved controversial. Other research groups, using different telescopes and analysis techniques, sometimes found no evidence for changing constants. Some studies even suggested changes in the opposite direction. The measurements required extraordinary precision, pushing ground-based telescopes to their limits. Systematic errors from atmospheric effects, instrumental calibration, and data analysis procedures could potentially mimic the signals the researchers were trying to detect. The controversy deepened when different research groups began reporting conflicting results from the same or similar datasets. Some found evidence for increasing fine structure constant in one direction of the sky, but not in others, suggesting that fundamental constants might vary not just with time, but also with position in the universe. This raised the possibility that we live in a region of space where physical laws are different from those in other parts of the cosmos. Independent confirmation came from an unexpected source: natural nuclear reactors. Approximately 2 billion years ago, in what is now Gabon, Africa, conditions were just right for natural uranium deposits to achieve critical mass and begin nuclear fission reactions. These natural reactors operated for hundreds of thousands of years, leaving behind distinctive isotopic signatures in the surrounding rock. The nuclear reaction rates depend on fundamental constants, so the isotope ratios provide a snapshot of physical laws as they existed 2 billion years ago. Analysis of samples from the Oklo natural reactor suggested that the fine structure constant had indeed been different in the past, though the magnitude and direction of the change remained uncertain. The nuclear physics involved is complex, and different isotopic ratios can be affected by various processes. making it difficult to isolate the effects of changing fundamental constants from other geological and nuclear processes. Laboratory experiments have also contributed to the search for evidence of changing constants. Ultra-precise atomic clocks, accurate to better than 1 part in 10 to the 18th power, can detect tiny drifts in atomic transition frequencies over periods of months or years. These experiments compare different types of atomic transitions, looking for any systematic changes that might indicate varying fundamental constants. Some atomic clock experiments have reported small but statistically significant drifts in transition frequency ratios over time periods of several years. However, these results are at the very edge of experimental precision, and it remains unclear whether the observed drifts represent genuine changes in fundamental constants or subtle systematic effects in the experimental apparatus. Cosmic microwave background observations have provided another window into the early universe. This radiation, the afterglow of the Big Bang, carries information about physical conditions when the universe was only 380,000 years old. Detailed analysis of temperature fluctuations in this radiation can constrain how fundamental constants might have evolved since that early epoch. Studies of the cosmic microwave background have generally found no evidence for large changes in fundamental constants since the universe became transparent to radiation. However, these observations primarily constrain changes over the past 13 billion years and cannot rule out small variations or changes that occurred even earlier in cosmic history. Perhaps the most intriguing evidence comes from studies of distant supernovae, the explosive deaths of massive stars. These cosmic explosions are so bright that they can be observed across billions of light years, providing standard candles for measuring cosmic distances and the expansion rate of the universe. If the speed of light has been changing, it could affect how we interpret the light curves and spectra of these distant explosions. Some researchers have suggested that the apparent acceleration of cosmic expansion, discovered through supernova observations in the late 1990s, might be partially explained by changing fundamental constants rather than mysterious dark energy. If the speed of light was larger in the past, distant supernovae would appear dimmer than expected, potentially mimicking the effects of accelerated expansion. Gravitational wave detectors like LIGO have opened another avenue for testing the constancy of light speed. These instruments measure tiny distortions in spacetime caused by colliding black holes and neutron stars. The gravitational waves themselves travel at the speed of light, so any changes in this fundamental constant would affect the timing and characteristics of the signals we detect. Early results from gravitational wave astronomy have generally supported the constancy of light speed, but the field is still young. As more sensitive detectors come online and we observe gravitational waves from more distant sources, these measurements may provide increasingly stringent tests of whether fundamental constants have remained unchanged over cosmic time. The search for evidence of changing light speed has also extended to studies of gamma-ray bursts, the most energetic explosions in the universe. These events release more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifetime. The gamma rays from these distant explosions travel for billions of years through intergalactic space before reaching Earth. If the speed of light depends on photon energy, high-energy gamma rays and low-energy radio waves from the same burst might arrive at Earth at slightly different times, even though they were emitted simultaneously. Several studies have looked for such arrival time differences in gamma-ray burst observations, with mixed results. Some have claimed to detect small time delays that could indicate energy-dependent light speed, while others have found no such effects. The evidence for a changing speed of light remains tantalizing but inconclusive. Each measurement pushes against the limits of current technology, and systematic errors can easily mimic the tiny signals that researchers are trying to detect. Yet the accumulated weight of observations from multiple independent approaches suggests that our assumption of constant fundamental constants may be worth questioning. Could the speed of light be slowing down? Could this subtle change be woven into the very fabric of the universe, unseen yet profound, affecting everything from the structure of atoms to the expansion of space itself? When physicists first began to seriously consider the possibility that the speed of light might not be constant, they faced a profound challenge. How could such a fundamental pillar of modern physics vary without bringing down the entire theoretical structure built upon it? The answer lay in developing new mathematical frameworks that could accommodate changing constants while preserving the essential insights of relativity and quantum mechanics. The pioneering work in this field came from Brazilian physicist João Magejo and British cosmologist Andreas Albrecht in the late 1990s. They proposed what became known as varying speed of light cosmology, or VSL theory. Their radical idea suggested that the speed of light was much larger in the early universe and has been gradually decreasing ever since. This seemingly simple change had profound implications for our understanding of cosmic evolution. In traditional cosmology, the horizon problem plagued scientists for decades. When we observe the cosmic microwave background radiation, we see that distant regions of the sky have almost exactly the same temperature, even though they are so far apart that light has never had time to travel between them since the Big Bang. How could these regions have reached thermal equilibrium if they could never communicate? The standard answer involves cosmic inflation, a period of exponential expansion in the first fraction of a second after the universe began. VSL cosmology offered an elegant alternative explanation. If light traveled much faster in the early universe, then regions that appear disconnected today could have been in causal contact when the cosmos was young. As the universe evolved and the speed of light decreased, these regions became isolated from each other, but they retained the thermal equilibrium established when faster light allowed communication across vast distances. The mathematical framework of VSL theory required careful construction to avoid inconsistencies with well-established physics. Magejo and Albrecht developed models where the speed of light varies in a specific way that preserves the essential structure of Einstein's equations, while allowing for temporal evolution of this fundamental constant. They showed that such theories could explain several puzzling features of our universe without requiring exotic concepts like inflation or dark energy. Building on this foundation, cosmologists began exploring various mechanisms that could drive changes in the speed of light. One promising approach involved scalar fields, hypothetical quantities that permeate all of space and can vary in strength over time. These fields are similar to the Higgs field that gives particles their mass, but instead of affecting mass, they would influence the speed of light and other fundamental constants. Scalar field models provided a natural way for fundamental constants to evolve slowly over cosmic time. As the universe expands and cools, the scalar field could settle into different energy states, causing the speed of light to change gradually. These models predicted specific patterns for how light speed should vary, allowing astronomers to test the theories against observations of distant quasars and other cosmic phenomena. String theory, the ambitious attempt to unify all fundamental forces into a single mathematical framework, also suggested ways that fundamental constants could vary. In string theory, the fundamental particles we observe are actually tiny vibrating strings in a higher dimensional space. The properties of these strings, including how they relate to the speed of light, depend on the geometry of the extra dimensions we cannot directly perceive. If the extra dimensions predicted by string theory are slowly changing size or shape, this could cause observable constants in our three-dimensional world to vary over time. String theorists developed models where the compactification of extra dimensions drives changes in fundamental constants, providing a deep theoretical foundation for VSL theories rooted in our most sophisticated understanding of quantum gravity. The Brane-World scenario, another outgrowth of string theory, offered yet another mechanism for varying constants. In these models, our entire universe exists as a three-dimensional membrane, or brane, floating in a higher dimensional space called the bulk. Fundamental constants could vary if our brane is moving through the bulk, or if the bulk itself is evolving over time. Brane-World cosmology suggested that what we perceive as fundamental constants might actually be composite quantities that depend on our brane's position and orientation in the higher dimensional bulk. As cosmic evolution carries our brane along different trajectories through this space, the effective values of constants like the speed of light could change in ways that would be observable through precision astronomical measurements. Quantum gravity theories provided another avenue for understanding varying constants. At the smallest scales of space and time, near the Planck length of 10 to the negative 35 meters and the Planck time of 10 to the negative 43 seconds, quantum effects become so strong that space and time themselves might fluctuate randomly. These quantum fluctuations could cause fundamental constants to vary slightly, with the variations becoming more pronounced over cosmic timescales. Loop quantum gravity, an alternative approach to quantum gravity that does not require extra dimensions, suggested that space itself might be granular at the smallest scales, composed of discrete units rather than being perfectly continuous. In such theories, the speed of light could depend on the size and properties of these fundamental space grains, which might evolve as the universe expands and ages. Causal dynamical triangulation, another approach to quantum gravity, modeled spacetime as a network of simple geometric building blocks that can rearrange themselves over time. In these models, the effective speed of light emerges from the connectivity and topology of the network, providing a mechanism for this apparently fundamental constant to vary as the network evolves. The challenge for all VSL theories was to make specific, testable predictions while avoiding conflicts with well-established experimental results. Any successful theory had to explain why laboratory measurements over human timescales show constant light speed while allowing for variations over cosmic timescales. This required careful attention to the rates of change and the mechanisms that drive variability. Some VSL models predicted that the rate of change should be proportional to the expansion rate of the universe, meaning that fundamental constants evolved most rapidly in the early cosmos and are changing very slowly today. Others suggested that changes might be episodic, occurring primarily during phase transitions or other special epochs in cosmic history. The relationship between changing light speed and other fundamental constants proved crucial for developing realistic models. The fine structure constant, which determines the strength of electromagnetic interactions, depends on the speed of light, the elementary electric charge, and Planck's constant. If light speed changes, at least one of the other quantities must also change to maintain consistency with observations. Different VSL theories made different assumptions about which constants vary and which remain fixed. Some models allowed only the speed of light to change, requiring careful mathematical treatment to avoid inconsistencies. Others permitted multiple constants to evolve together in coordinated ways that preserved the essential physics while allowing for cosmic evolution. The dimensional analysis of fundamental constants revealed deep connections between seemingly unrelated quantities. The speed of light has dimensions of length divided by time, while the fine structure constant is dimensionless. Any theory that changes the speed of light must address how this affects measurements of distance, time, and energy, ensuring that the resulting physics remains mathematically consistent. VSL theories also had to confront the problem of units and measurement. If the speed of light is changing, how would we detect this change when our standard units of length and time are themselves defined in terms of light speed? This measurement problem required sophisticated theoretical analysis to identify observable quantities that could reveal varying constants, despite our dependence on those same constants for measurement. Advanced VSL models incorporated quantum field theory effects, considering how changing light speed would affect the quantum vacuum and the behavior of virtual particles. These effects could provide additional observational signatures and help distinguish between different theoretical approaches to varying constants. The cosmological implications of VSL theories extended far beyond explaining the horizon problem. If light speed was larger in the past, this could affect calculations of the universe's age, the distances to remote galaxies, and the timeline of cosmic evolution. Some VSL models suggested that the universe might be significantly older than current estimates based on constant light speed. Dark energy, the mysterious force causing cosmic expansion to accelerate, might also be connected to varying fundamental constants. Some theorists proposed that what we interpret as dark energy could actually be the effect of slowly changing light speed or other constants, providing a more fundamental explanation for cosmic acceleration than hypothetical vacuum energy. The theoretical landscape of VSL cosmology continues to evolve as physicists develop increasingly sophisticated models that can account for all known observations while making predictions for future experiments. These theories represent some of the most ambitious attempts to understand the deepest foundations of physical reality. If the speed of light changes, it could rewrite the laws of physics as we know them. But is there enough evidence to change the theory, to accept that our most fundamental constant might itself be variable? Deep within the heart of every atom lies a number that has puzzled physicists for over a century. It appears to have no units, no dimensions, and yet it governs some of the most fundamental processes in the universe. This mysterious quantity is known as the fine structure constant, represented by the Greek letter alpha. and its value is approximately 1 divided by 137.036. This seemingly arbitrary number holds the key to understanding whether the speed of light has been changing throughout cosmic history. The fine structure constant was first discovered in 1916 by German physicist Arnold Sommerfeld when he was trying to explain the detailed structure of hydrogen's spectral lines. When hydrogen gas is heated or excited by electricity, it glows with specific colors corresponding to very precise wavelengths of light. These spectral lines had been mapped with extraordinary precision, but early quantum theory could only explain their approximate positions, not their fine details. Sommerfeld found that each major spectral line was actually split into several closely spaced lines, creating what he called the fine structure of atomic spectra. The spacing between these fine structure components was proportional to a fundamental combination of physical constants, the square of the elementary electric charge, divided by the product of Planck's constant and the speed of light, all multiplied by appropriate factors to make the result dimensionless. This combination of constants, the fine structure constant, determines the strength of electromagnetic interactions between charged particles. It governs how tightly electrons are bound to atomic nuclei, how efficiently atoms absorb and emit light, and even the probability that a photon will interact with matter. Despite its fundamental importance, the fine structure constant is a pure number, independent of any human choice of units or measurement systems. The remarkable thing about the fine structure constant is that it appears to be perfectly tuned for the existence of complex chemistry and life as we know it. If alpha were significantly larger, electrons would be bound so tightly to nuclei that chemical bonds could not form easily. If it were much smaller, electrons would be bound so weakly that atoms would be unstable, and molecules could not exist. The value we observe seems to fall within a narrow range that allows for the rich complexity of matter we see around us. This apparent fine-tuning has led some physicists to wonder whether the fine structure constant might have evolved over cosmic time, perhaps starting with a different value in the early universe and gradually changing to reach its current life-permitting value. If true, this would suggest that fundamental constants are not truly constant, but are instead slowly evolving features of cosmic development. The connection between the fine structure constant and the speed of light is intimate and profound. Alpha equals the square of the elementary electric charge, divided by 4 pi times the electric permittivity of free space, times Planck's constant, times the speed of light. This means that any change in the speed of light must be accompanied by changes in other fundamental quantities if the fine structure constant is to remain constant, or alternatively, a changing speed of light could cause the fine structure constant itself to vary. Modern precision spectroscopy has revealed that the fine structure constant can be measured with extraordinary accuracy using atomic transitions. Different types of atomic transitions have different sensitivities to alpha, so by comparing multiple atomic clocks based on different elements, scientists can detect tiny variations in the fine structure constant over time periods of months or years. Laboratory experiments using trapped ions cooled to near absolute zero have achieved remarkable precision in measuring atomic transition frequencies. These experiments compare transitions in different atoms that have different dependencies on the fine structure constant. If alpha were changing over time, the frequency ratios between different atomic transitions would drift in predictable ways, providing a sensitive test of constant variation. The most precise laboratory limits on fine structure constant variation come from comparing atomic clocks based on different elements over periods of several years. These experiments have shown that if alpha is changing, it must be doing so at a rate of less than 1 part in 10 to the 17th power per year. This incredibly small limit demonstrates the extraordinary stability of fundamental constants over human timescales. However, laboratory experiments can only probe changes over relatively short time periods. To investigate whether the fine structure constant has varied over cosmic history, astronomers must turn to observations of distant astronomical objects whose light has been traveling for billions of years. This ancient light carries information about the values of fundamental constants when it was emitted. The most sensitive astronomical tests involve studying absorption lines in the spectra of distant quasars. As quasar light travels through intervening gas clouds, atoms in these clouds absorb photons at very specific wavelengths that depend on atomic energy levels. These energy levels, in turn, depend on the fine structure constant through complex quantum mechanical calculations. Different atomic transitions have different sensitivities to changes in alpha. Some transitions become more widely separated if the fine structure constant increases, while others become more closely spaced. By comparing multiple transitions from the same gas cloud, astronomers can determine whether the fine structure constant had a different value when that light was absorbed billions of years ago. The alkali doublet method represents one of the most powerful techniques for detecting fine structure constant variation. Alkali atoms like sodium have pairs of spectral lines called doublets, where the separation between the two lines is directly proportional to the square of the fine structure constant. By measuring the doublet separations in distant gas clouds and comparing them with laboratory measurements, astronomers can probe alpha variation with high sensitivity. Many atom method analysis takes this approach even further by simultaneously analyzing dozens of different absorption lines from multiple elements in the same gas cloud. Each transition has a different calculated sensitivity to fine structure constant variation, so this technique can detect incredibly small changes while providing built-in checks against systematic errors. The results from astronomical fine structure constant measurements have been tantalizing but controversial. Some studies have reported evidence for small variations in alpha over cosmic time, typically at the level of a few parts per million over billions of years. Other analyses of similar or even identical data have found no evidence for variation, highlighting the extreme difficulty of these measurements. One of the most intriguing claims came from analysis of absorption systems along the line of sight to distant quasars. This study suggested that the fine structure constant might have been smaller in the past by about 6 parts per million when the universe was half its current age. If confirmed, this would indicate that the fine structure constant has been slowly increasing over cosmic time. However, subsequent analyses using different telescopes, improved data reduction techniques, and more sophisticated statistical methods have sometimes reached different conclusions. Some studies find no evidence for fine structure constant variation, while others suggest changes in the opposite direction. The measurements are at the very edge of current observational capabilities, making systematic errors a constant concern. The possibility of spatial variation in fundamental constants has added another layer of complexity to these studies. Some researchers have reported hints that the fine structure constant might have different values in different directions of the sky, suggesting that fundamental physics itself might vary from place to place in the universe. Such variation would have profound implications for our understanding of the cosmos and the universality of physical laws. White dwarf stars provide another laboratory for testing fine structure constant variation over cosmic time. These stellar remnants are supported against gravitational collapse by electron degeneracy pressure, which depends sensitively on atomic physics and thus on the fine structure constant. The masses and cooling ages of white dwarf stars can constrain how alpha has evolved over the past several billion years. Comparison of primordial element abundances with predictions from Big Bang nucleosynthesis offers yet another approach to constraining fine structure constant variation. The nuclear reaction rates that determined how much hydrogen, helium, and lithium were produced in the early universe depend on fundamental constants, including alpha. Discrepancies between observed and predicted abundances could indicate that constants had different values during nucleosynthesis. The cosmic microwave background radiation carries information about physical conditions when the universe was only 380,000 years old. The details of how matter and radiation interacted during this epoch depend on atomic physics, and thus on the fine structure constant. Precision measurements of temperature fluctuations in this ancient light can constrain how alpha has evolved since recombination. Laboratory tests of the equivalence principle provide additional constraints on fine structure constant variation. Einstein's general theory of relativity predicts that all forms of energy contribute equally to gravitational mass. If the fine structure constant were changing, the binding energies of different atomic nuclei would change at different rates, potentially causing violations of the equivalence principle that could be detected with sensitive experiments. Molecular spectroscopy offers some of the most sensitive probes of fine structure constant variation. Molecules have complex spectra with transitions that depend on alpha in different ways. Radio observations of molecular absorption lines in distant galaxies can potentially detect fine structure constant changes with extraordinary precision, though the analysis requires sophisticated quantum chemical calculations. The interpretation of fine structure constant measurements depends critically on understanding which other fundamental constants might also be varying. If multiple constants change simultaneously, their effects on atomic spectra can partially cancel out, making variations harder to detect. Theoretical models must specify how different constants evolve together to make meaningful predictions for observations. Clock comparison experiments using different atomic species provide model-independent tests of fundamental constant stability. By monitoring multiple atomic clocks simultaneously over extended periods, these experiments can detect correlated drifts that might indicate varying constants, while rejecting systematic effects that would affect individual clocks differently. The fine structure constant holds a delicate balance in the universe, governing the strength of electromagnetic interactions that bind atoms together and determine the properties of matter. Could it be shifting, pulling the speed of light along with it, as cosmic evolution slowly reshapes the fundamental parameters that define physical reality? When we look up at the night sky, we are looking backward through time. The light from distant stars and galaxies has been traveling through space for thousands, millions, or even billions of years before reaching our eyes. This ancient light carries within it a record of physical conditions that existed when it began its cosmic journey, potentially preserving evidence of how fundamental constants like the speed of light have evolved over the history of the universe. The nearest star to our Sun, Proxima Centauri, is about 4.25 light-years away. This means that when we observe it tonight, we are seeing it as it existed 4 years and 3 months ago. The light from the Andromeda Galaxy, our nearest large galactic neighbor, left that galaxy 2.5 million years ago, when our human ancestors were just beginning to use stone tools. But astronomers can observe objects much more distant than Andromeda, peering back to times when the universe itself was young. The most distant galaxies visible to our largest telescopes appear as they existed when the universe was less than 1 billion years old, only about 7% of its current age of 13.8 billion years. The light from these primordial galaxies has been traveling for over 12 billion years, crossing an almost unimaginable expanse of space and time. If the speed of light has been changing during this cosmic journey, these ancient photons might carry subtle signatures of that variation. Quasars represent some of the most powerful and distant light sources in the universe. These brilliant objects are the active centers of galaxies, powered by supermassive black holes that can contain billions of times the mass of our Sun. As matter spirals into these cosmic giants, it heats to millions of degrees and radiates energy across the entire electromagnetic spectrum. Some quasars are so luminous that they outshine all the stars in their host galaxies combined, making them visible across most of the observable universe. The light from quasars provides an ideal laboratory for studying fundamental constants over cosmic time. These distant beacons are bright enough to produce detailed spectra, even when observed from billions of light years away. Their light passes through multiple gas clouds during its journey to Earth, and each cloud imprints its own absorption fingerprint on the quasar spectrum. By analyzing these absorption features, astronomers can probe the physical conditions in the early universe. Absorption line spectroscopy forms the foundation of these investigations. When quasar light encounters a gas cloud, atoms in the cloud absorb photons at very specific wavelengths, corresponding to electronic transitions within the atoms. Different elements produce characteristic patterns of absorption lines, creating what astronomers call the cosmic barcode. This barcode contains information about the composition, temperature, density, and motion of the intervening gas. The wavelengths of these absorption lines depend on fundamental constants through the quantum mechanical equations that govern atomic structure. The fine structure constant determines the strength of electromagnetic interactions within atoms, affecting the precise energies of electronic transitions. If fundamental constants had different values when the light was absorbed, the absorption lines would appear at slightly different wavelengths than we observe in laboratory experiments today. The Lyman alpha forest represents one of the most important features in distant quasar spectra. This forest consists of hundreds of absorption lines created by hydrogen gas clouds at various distances along the line of sight to each quasar. Each line corresponds to the Lyman alpha transition of hydrogen, the most abundant element in the universe. The forest extends across a wide range of wavelengths because gas clouds at different distances have different redshifts due to cosmic expansion. By analyzing the detailed structure of the Lyman alpha forest, astronomers can map the distribution of matter in the early universe and test whether fundamental constants have remained unchanged over cosmic time. The precise wavelengths of these absorption features provide a sensitive probe of atomic physics billions of years ago, allowing researchers to compare ancient and modern values of fundamental constants. Metal line systems offer even more sensitive tests of fundamental constant variation. Despite the astronomical terminology, metals in this context refer to any element heavier than hydrogen and helium. These elements were forged in the nuclear furnaces of stars and dispersed into space through stellar winds and supernova explosions. Gas clouds, enriched with metals, produce complex absorption spectra with dozens or hundreds of individual lines. Different metal transitions have different sensitivities to changes in fundamental constants. Some transitions become more widely separated if the fine structure constant increases, while others become more closely spaced. By comparing multiple transitions from the same gas cloud, astronomers can determine whether fundamental constants had different values when that light was absorbed billions of years ago. The many multiplet method represents the most sophisticated approach to these measurements. This technique simultaneously analyzes dozens of absorption lines from multiple elements in the same absorbing system. Each transition has a theoretically calculated sensitivity to fundamental constant variation, allowing astronomers to fit for changes in alpha, while accounting for systematic effects like wavelength calibration errors and velocity structure within the gas clouds. Systematic uncertainties pose the greatest challenge in these measurements. Ground-based telescopes must observe through Earth's atmosphere, which introduces wavelength distortions that can mimic the signals astronomers are trying to detect. Instrumental effects in the spectrographs can also shift line positions by amounts comparable to the tiny variations being sought. Even the motions of gas clouds themselves can complicate the analysis if not properly accounted for. The most precise measurements require extraordinary attention to wavelength calibration. Astronomers use hollow cathode lamps filled with known gases to provide reference spectra with precisely measured line positions. These calibration spectra are obtained immediately before and after each quasar observation to track any instrumental drifts. Advanced analysis techniques can achieve wavelength precisions of a few meters per second, comparable to the precision needed to detect planets orbiting other stars. Atmospheric effects present another significant challenge. Earth's atmosphere is constantly in motion, with temperature variations and pressure changes that alter the refractive index and thus the apparent wavelengths of spectral lines. Adaptive optics systems can partially compensate for atmospheric turbulence, but residual effects can still introduce systematic errors at the level of sensitivity required for fundamental constant measurements. Space-based observations offer the potential to eliminate atmospheric effects entirely, but they bring their own challenges. The Hubble Space Telescope has been used for some of the most precise quasar spectroscopy studies, but even space-based instruments suffer from thermal variations, mechanical flexure, and other effects that can influence wavelength calibration at the micrometer per second level needed for these measurements. Statistical analysis techniques have become increasingly sophisticated as astronomers have developed better methods for extracting weak signals from noisy data. Monte Carlo simulations help evaluate the significance of apparent variations by generating thousands of synthetic datasets with known properties. Machine learning algorithms can identify subtle patterns in spectra that might indicate fundamental constant variation while rejecting spurious signals caused by systematic effects. The redshift evolution of absorption systems provides crucial information about how the universe has changed over cosmic time. Gas clouds at higher redshifts are observed at earlier epochs in cosmic history, when the universe was denser, hotter, and contained fewer heavy elements. By studying absorption systems across a wide range of redshifts, astronomers can trace the evolution of fundamental constants from the early universe to the present day. Damped Lyman alpha systems represent some of the most important targets for these studies. These systems contain large columns of neutral hydrogen gas and are thought to be the progenitors of present-day galaxies. They provide clean laboratories for studying fundamental constants because the gas is relatively simple and well understood compared to the complex environments around active galactic nuclei. Subdamped Lyman alpha systems offer complementary information about fundamental constant evolution. These systems contain smaller amounts of neutral hydrogen, but are more numerous than damped systems, providing better statistical sampling across cosmic time. They also tend to have different metallicities and physical conditions, allowing tests of whether fundamental constant variation depends on local environment. Gamma-ray bursts provide another avenue for probing fundamental constants over cosmic distances. These energetic explosions produce afterglows that can be observed across most of the visible universe. The spectra of gamma-ray burst afterglows sometimes show metal absorption lines that can be analyzed using the same techniques developed for quasar spectroscopy. The advantage of gamma-ray burst spectroscopy is that these objects are observed at the moment of explosion, providing a precise timestamp for when the absorption occurred. This eliminates some of the complications that arise when analyzing quasar spectra, where the absorbing gas might have complex velocity structure or evolving physical conditions. Gravitationally lensed quasars offer unique opportunities for fundamental constant studies. When a massive galaxy lies along the line of sight to a distant quasar, its gravitational field can bend and focus the quasar light, creating multiple images of the same object. These images follow slightly different paths through space, allowing astronomers to probe different regions of the intervening galaxy and test whether fundamental constants vary with position as well as time. Radio astronomy provides complementary information about fundamental constants through observations of molecular absorption lines. Molecules have more complex spectra than atoms, with rotational and vibrational transitions that depend on fundamental constants in different ways. Radio telescopes can observe molecular absorption in distant galaxies with extraordinary precision, potentially detecting fundamental constant variations that might be missed by optical studies. The 21 centimeter line of neutral hydrogen offers another powerful probe of fundamental constants. This radio transition occurs when the electron in a hydrogen atom flips its spin relative to the proton, producing a photon with a wavelength of 21.1 centimeters. The frequency of this transition depends on fundamental constants through the magnetic properties of the proton and electron. Future radio telescopes like the Square Kilometre Array will be capable of detecting 21 centimeter absorption from neutral hydrogen throughout most of the observable universe. These observations will provide an independent test of fundamental constant evolution that complements optical studies of metal absorption lines in quasar spectra. What does ancient light tell us? Could it reveal the subtle changes in the speed of light, tracing the cosmos's evolution through billions of years of cosmic history, preserving in its spectrum the fingerprints of a universe where fundamental constants themselves evolve? Chapter 7. Experimental evidence and attempts to measure light speed over time. In the pursuit of understanding whether the speed of light changes over time, scientists have devised increasingly ingenious experiments that push the boundaries of measurement precision. These investigations require techniques so sensitive that they can detect changes smaller than the width of a proton over distances spanning the entire observable universe. The challenge lies not just in achieving such extraordinary precision, but in distinguishing genuine variations in fundamental constants from the countless sources of systematic error that plague any ultra-precise measurement. Modern atomic clocks represent the pinnacle of timekeeping precision, capable of measuring time with accuracies better than 1 part in 10 to the 18th power. These remarkable devices work by counting the oscillations of atoms transitioning between different energy levels, effectively using the atom itself as a tiny pendulum. The frequencies of these atomic transitions depend on fundamental constants, including the fine structure constant, and thus indirectly on the speed of light. The most precise atomic clocks use single ions trapped in electromagnetic fields and cooled to temperatures just a few millionths of a degree above absolute zero. At these extreme conditions, the thermal motion of the atoms is nearly eliminated, allowing scientists to measure atomic transition frequencies with unprecedented accuracy. These clocks are so stable that they would gain or lose less than 1 second over the entire age of the universe. Clock comparison experiments form the foundation of modern tests for varying fundamental constants. By simultaneously operating multiple atomic clocks based on different elements, scientists can monitor the ratios of atomic transition frequencies over extended periods. If fundamental constants were changing, different atomic transitions would be affected differently, causing the frequency ratios to drift in predictable ways. The most sensitive laboratory tests compare clocks based on different atomic species, with varying sensitivities to fundamental constant changes. For example, cesium clocks are relatively insensitive to changes in the fine structure constant, while ytterbium ion clocks show much stronger dependence. By comparing these clocks over periods of months or years, researchers can place stringent limits on how rapidly fundamental constants might be evolving. One of the most ambitious clock comparison experiments involves a network of atomic clocks distributed around the world. This global network allows scientists to search for both temporal variations in fundamental constants and possible spatial variations that might occur if physical laws differ slightly from place to place. The clocks are connected through fiber optic links and satellite communications, enabling real-time comparisons with extraordinary precision. The challenges of maintaining such precision over extended periods are immense. Environmental factors like temperature fluctuations, magnetic field variations, and mechanical vibrations can all affect atomic transition frequencies at levels comparable to the tiny changes that might indicate varying fundamental constants. Researchers must carefully control and monitor every aspect of the experimental environment to achieve the required stability. Systematic effects pose the greatest threat to these ultra-precise measurements. The frequency of an atomic transition can be shifted by external electric and magnetic fields, collisions with other atoms, and even the motion of the atom itself due to recoil from absorbed or emitted photons. Each of these effects must be measured and corrected with extraordinary accuracy to avoid mistaking systematic shifts for genuine fundamental constant variation. Laser interferometry provides another approach to testing the constancy of the speed of light. These experiments use lasers to measure tiny changes in distance by monitoring the interference patterns created when light beams travel along different paths. The most sensitive interferometers can detect distance changes smaller than 1/10,000th the width of a proton, making them exquisitely sensitive to any variations in light speed. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, represents the ultimate achievement in laser interferometry. LIGO uses 4-kilometer-long arms to detect gravitational waves. By measuring tiny changes in the distance, light travels along perpendicular directions. While designed primarily to detect gravitational waves, LIGO's extraordinary sensitivity also makes it capable of testing whether the speed of light remains constant over time. LIGO's measurements span multiple years of continuous operation, providing a sensitive test of light speed constancy over human timescales. Any variation in the speed of light would affect the round-trip travel time of laser beams in the interferometer arms, potentially creating detectable signals. The absence of such signals places stringent limits on how rapidly light speed could be changing in the present epoch. Cavity resonator experiments offer yet another approach to testing fundamental constant stability. These devices confine electromagnetic radiation in precisely machined metal cavities, creating standing wave patterns whose frequencies depend on the cavity dimensions and the speed of light. By monitoring the resonant frequencies of multiple cavities made from different materials, scientists can search for variations in fundamental constants. The most sensitive cavity experiments use superconducting resonators cooled to liquid helium temperatures to minimize thermal noise and frequency drift. These devices can maintain their resonant frequencies with stabilities approaching 1 part in 10 to the 16th power over periods of days or weeks. Comparing resonators made from different materials provides a test of whether fundamental constants are changing uniformly or whether different materials respond differently to such changes. Frequency comb technology has revolutionized precision spectroscopy and enabled new tests of fundamental constant variation. A frequency comb is a laser system that produces a series of precisely spaced frequency components, creating a ruler for measuring optical frequencies with extraordinary accuracy. These devices can link optical atomic transitions to microwave frequency standards, enabling clock comparisons across different parts of the electromagnetic spectrum. The development of optical frequency combs earned their inventors the 2005 Nobel Prize in Physics and opened new possibilities for fundamental constant tests. By using frequency combs to compare optical atomic clocks with microwave atomic clocks, scientists can search for variations in the ratio of these frequencies that might indicate changing fundamental constants. Molecular spectroscopy experiments provide complementary tests of fundamental constant stability. Molecules have complex internal structures, with vibrational and rotational energy levels that depend on fundamental constants in different ways than atomic transitions. High-resolution molecular spectroscopy can achieve frequency measurement precisions comparable to atomic clocks while probing different combinations of fundamental constants. Precision tests using molecular hydrogen are particularly important because this simple molecule can be studied with exceptional theoretical accuracy. The energy levels of hydrogen molecules depend on the proton-to-electron mass ratio and other fundamental constants in ways that can be calculated precisely using quantum mechanics. Laboratory measurements of molecular hydrogen transition frequencies provide sensitive tests of whether these constants have remained stable over the duration of the experiments. Neutron interferometry offers a unique approach to testing fundamental constants through quantum mechanical experiments with matter waves. When neutrons are split into two beams that travel along different paths and then recombined, they create interference patterns that depend on the fundamental constants that govern neutron interactions. These experiments can probe aspects of fundamental physics that are not accessible through electromagnetic measurements alone. The most precise neutron interferometry experiments use ultra-cold neutrons trapped in magnetic bottles or gravitational wells. These techniques allow scientists to study neutron properties with extraordinary precision over extended periods, searching for any variations that might indicate changing fundamental constants. The results complement electromagnetic tests by probing different aspects of fundamental physics. Precision tests of the equivalence principle provide indirect constraints on fundamental constant variation. Einstein's general theory of relativity predicts that all forms of energy contribute equally to gravitational mass. If fundamental constants were changing, the binding energies of different atomic nuclei would change at different rates, potentially causing violations of the equivalence principle that could be detected with sensitive gravitational experiments. The most precise equivalence principle tests use torsion balances to compare the gravitational attractions of different materials with extraordinary accuracy. These experiments can detect fractional differences in gravitational acceleration as small as 1 part in 10 to the 13th power, providing sensitive tests of whether different materials respond identically to gravitational fields. Laboratory tests of special relativity provide additional constraints on fundamental constant variation. These experiments verify that the speed of light is the same in all directions and for all observers, as required by Einstein's theory. Modern versions of the Michelson-Morley experiment use laser interferometry and rotating platforms to search for any anisotropy in light speed, with sensitivities far exceeding the original experiment. Tests of time reversal invariance and other fundamental symmetries also constrain how fundamental constants might vary. If constants were changing over time, this could violate certain symmetry principles that are believed to be exact in nature. Precision measurements of atomic and nuclear properties can search for violations of these symmetries that might indicate varying constants. The most ambitious experimental programs combine multiple complementary approaches to maximize sensitivity to fundamental constant variation. By simultaneously operating atomic clocks, laser interferometers, cavity resonators, and other precision instruments, scientists can search for correlated changes that might indicate genuine, fundamental, constant variation, while rejecting systematic effects that would affect individual experiments differently. International collaborations have become essential for achieving the highest precision in these measurements. Different research groups around the world operate similar experiments under different conditions, providing crucial cross-checks and reducing the likelihood that systematic effects could be mistaken for genuine signals. The results from these diverse experimental approaches provide increasingly stringent constraints on fundamental constant variation. Future experimental developments promise even greater sensitivity to fundamental constant changes. New atomic clock technologies using nuclear transitions, improved laser stabilization techniques, and novel approaches to quantum state manipulation may enable detection of fundamental constant variations at levels currently beyond experimental reach. Space-based experiments offer the potential to eliminate many sources of systematic error that plague ground-based measurements. The microgravity environment of spacecraft reduces mechanical disturbances, while the absence of atmosphere eliminates many sources of electromagnetic interference. Several space missions dedicated to fundamental physics tests are currently in development or under consideration. In the pursuit of truth, scientists look to experiments to reveal the fundamental nature of reality. But measuring the speed of light over cosmic timescales is no simple task, requiring precision that pushes the very limits of what technology and human ingenuity can achieve. In the pursuit of understanding whether the speed of light changes over time, scientists have devised increasingly ingenious experiments that push the boundaries of measurement precision. These investigations require techniques so sensitive that they can detect changes smaller than the width of a proton over distances spanning the entire observable universe. The challenge lies not just in achieving such extraordinary precision, but in distinguishing genuine variations in fundamental constants from the countless sources of systematic error that plague any ultra-precise measurement. Modern atomic clocks represent the pinnacle of timekeeping precision, capable of measuring time with accuracies better than 1 part in 10 to the 18th power. These remarkable devices work by counting the oscillations of atoms transitioning between different energy levels, effectively using the atom itself as a tiny pendulum. The frequencies of these atomic transitions depend on fundamental constants, including the fine structure constant, and thus indirectly on the speed of light. The most precise atomic clocks use single ions trapped in electromagnetic fields and cooled to temperatures just a few millionths of a degree above absolute zero. At these extreme conditions, the thermal motion of the atoms is nearly eliminated, allowing scientists to measure atomic transition frequencies with unprecedented accuracy. These clocks are so stable that they would gain or lose less than 1 second over the entire age of the universe. Clock comparison experiments form the foundation of modern tests for varying fundamental constants. By simultaneously operating multiple atomic clocks based on different elements, scientists can monitor the ratios of atomic transition frequencies over extended periods. If fundamental constants were changing, different atomic transitions would be affected differently, causing the frequency ratios to drift in predictable ways. The most sensitive laboratory tests compare clocks based on different atomic species with varying sensitivities to fundamental constant changes. For example, cesium clocks are relatively insensitive to changes in the fine structure constant, while ytterbium ion clocks show much stronger dependence. By comparing these clocks over periods of months or years, researchers can place stringent limits on how rapidly fundamental constants might be evolving. One of the most ambitious clock comparison experiments involves a network of atomic clocks distributed around the world. This global network allows scientists to search for both temporal variations in fundamental constants and possible spatial variations that might occur if physical laws differ slightly from place to place. The clocks are connected through fiber optic links and satellite communications, enabling real-time comparisons with extraordinary precision. The challenges of maintaining such precision over extended periods are immense. Environmental factors like temperature fluctuations, magnetic field variations, and mechanical vibrations can all affect atomic transition frequencies at levels comparable to the tiny changes that might indicate varying fundamental constants. Researchers must carefully control and monitor every aspect of the experimental environment to achieve the required stability. Systematic effects pose the greatest threat to these ultra-precise measurements. The frequency of an atomic transition can be shifted by external electric and magnetic fields, collisions with other atoms, and even the motion of the atom itself due to recoil from absorbed or emitted photons. Each of these effects must be measured and corrected with extraordinary accuracy to avoid mistaking systematic shifts for genuine fundamental constant variation. Laser interferometry provides another approach to testing the constancy of the speed of light. These experiments use lasers to measure tiny changes in distance by monitoring the interference patterns created when light beams travel along different paths. The most sensitive interferometers can detect distance changes smaller than 1/10,000th the width of a proton, making them exquisitely sensitive to any variations in light speed. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, represents the ultimate achievement in laser interferometry. LIGO uses 4-kilometer-long arms to detect gravitational waves. By measuring tiny changes in the distance, light travels along perpendicular directions. While designed primarily to detect gravitational waves, LIGO's extraordinary sensitivity also makes it capable of testing whether the speed of light remains constant over time. LIGO's measurements span multiple years of continuous operation, providing a sensitive test of light speed constancy over human timescales. Any variation in the speed of light would affect the round-trip travel time of laser beams in the interferometer arms, potentially creating detectable signals. The absence of such signals places stringent limits on how rapidly light speed could be changing in the present epoch. Cavity resonator experiments offer yet another approach to testing fundamental constant stability. These devices confine electromagnetic radiation in precisely machined metal cavities, creating standing wave patterns whose frequencies depend on the cavity dimensions and the speed of light. By monitoring the resonant frequencies of multiple cavities made from different materials, scientists can search for variations in fundamental constants. The most sensitive cavity experiments use superconducting resonators cooled to liquid helium temperatures to minimize thermal noise and frequency drift. These devices can maintain their resonant frequencies with stabilities approaching 1 part in 10 to the 16th power over periods of days or weeks. Comparing resonators made from different materials provides a test of whether fundamental constants are changing uniformly or whether different materials respond differently to such changes. Frequency comb technology has revolutionized precision spectroscopy and enabled new tests of fundamental constant variation. A frequency comb is a laser system that produces a series of precisely spaced frequency components, creating a ruler for measuring optical frequencies with extraordinary accuracy. These devices can link optical atomic transitions to microwave frequency standards, enabling clock comparisons across different parts of the electromagnetic spectrum. The development of optical frequency combs earned their inventors the 2005 Nobel Prize in Physics and opened new possibilities for fundamental constant tests. By using frequency combs to compare optical atomic clocks with microwave atomic clocks, scientists can search for variations in the ratio of these frequencies that might indicate changing fundamental constants. Molecular spectroscopy experiments provide complementary tests of fundamental constant stability. Molecules have complex internal structures with vibrational and rotational energy levels that depend on fundamental constants in different ways than atomic transitions. High-resolution molecular spectroscopy can achieve frequency measurement precisions comparable to atomic clocks while probing different combinations of fundamental constants. Precision tests using molecular hydrogen are particularly important because this simple molecule can be studied with exceptional theoretical accuracy. The energy levels of hydrogen molecules depend on the proton-to-electron mass ratio and other fundamental constants in ways that can be calculated precisely using quantum mechanics. Laboratory measurements of molecular hydrogen transition frequencies provide sensitive tests of whether these constants have remained stable over the duration of the experiments. Neutron interferometry offers a unique approach to testing fundamental constants through quantum mechanical experiments with matter waves. When neutrons are split into two beams that travel along different paths and then recombined, they create interference patterns that depend on the fundamental constants that govern neutron interactions. These experiments can probe aspects of fundamental physics that are not accessible through electromagnetic measurements alone. The most precise neutron interferometry experiments use ultra-cold neutrons trapped in magnetic bottles or gravitational wells. These techniques allow scientists to study neutron properties with extraordinary precision over extended periods, searching for any variations that might indicate changing fundamental constants. The results complement electromagnetic tests by probing different aspects of fundamental physics. Precision tests of the equivalence principle provide indirect constraints on fundamental constant variation. Einstein's general theory of relativity predicts that all forms of energy contribute equally to gravitational mass. If fundamental constants were changing, the binding energies of different atomic nuclei would change at different rates, potentially causing violations of the equivalence principle that could be detected with sensitive gravitational experiments. The most precise equivalence principle tests use torsion balances to compare the gravitational attractions of different materials with extraordinary accuracy. These experiments can detect fractional differences in gravitational acceleration as small as 1 part in 10 to the 13th power, providing sensitive tests of whether different materials respond identically to gravitational fields. Laboratory tests of special relativity provide additional constraints on fundamental constant variation. These experiments verify that the speed of light is the same in all directions and for all observers, as required by Einstein's theory. Modern versions of the Michelson-Morley experiment use laser interferometry and rotating platforms to search for any anisotropy in light speed, with sensitivities far exceeding the original experiment. Tests of time reversal invariance and other fundamental symmetries also constrain how fundamental constants might vary. If constants were changing over time, this could violate certain symmetry principles that are believed to be exact in nature. Precision measurements of atomic and nuclear properties can search for violations of these symmetries that might indicate varying constants. The most ambitious experimental programs combine multiple complementary approaches to maximize sensitivity to fundamental constant variation. By simultaneously operating atomic clocks, laser interferometers, cavity resonators, and other precision instruments, scientists can search for correlated changes that might indicate genuine fundamental constant variation while rejecting systematic effects that would affect individual experiments differently. International collaborations have become essential for achieving the highest precision in these measurements. Different research groups around the world operate similar experiments under different conditions, providing crucial cross-checks and reducing the likelihood that systematic effects could be mistaken for genuine signals. The results from these diverse experimental approaches provide increasingly stringent constraints on fundamental constant variation. Future experimental developments promise even greater sensitivity to fundamental constant changes. New atomic clock technologies using nuclear transitions, improved laser stabilization techniques, and novel approaches to quantum state manipulation may enable detection of fundamental constant variations at levels currently beyond experimental reach. Space-based experiments offer the potential to eliminate many sources of systematic error that plague ground-based measurements. The microgravity environment of spacecraft reduces mechanical disturbances, while the absence of atmosphere eliminates many sources of electromagnetic interference. Several space missions dedicated to fundamental physics tests are currently in development or under consideration. In the pursuit of truth, scientists look to experiments to reveal the fundamental nature of reality. But measuring the speed of light over cosmic timescales is no simple task, requiring precision that pushes the very limits of what technology and human ingenuity can achieve. If the speed of light is indeed slowing down over cosmic time, the implications would ripple through every aspect of our understanding of the universe. This seemingly simple change would force us to reconsider fundamental questions about the age of the cosmos, the distances to remote galaxies, the nature of time itself, and even our place within the grand cosmic story. The consequences would be so far-reaching that they would require a complete revision of our cosmic timeline and challenge some of our most cherished assumptions about the nature of reality. Consider first what a changing speed of light would mean for our measurements of cosmic distances. Astronomers determine the distances to faraway galaxies by observing how their light has been stretched and reddened by the expansion of the universe. This cosmic redshift depends on how long the light has been traveling and how much the universe has expanded during that journey. If light traveled faster in the past, photons from distant galaxies would have completed their journey in less time than we currently calculate. This would mean that distant galaxies are actually closer to us than our current measurements suggest. A galaxy that appears to be 10 billion light-years away, based on the assumption of constant light speed, might actually be significantly closer if light was moving faster when it began its journey. The entire cosmic distance ladder, the carefully calibrated series of measurements that allows us to map the universe, would need to be recalculated from the ground up. The implications for the age of the universe would be equally profound. Current estimates place the cosmos at 13.8 billion years old, calculated based on the rate of cosmic expansion and the assumption that fundamental constants have remained unchanged since the Big Bang. If the speed of light was larger in the past, light from the most distant observable objects would have traveled here more quickly than we assume, suggesting that the universe might be significantly older than our current estimates. Alternatively, if the changing speed of light affected the expansion rate itself, the universe might be younger than we think. The relationship between cosmic expansion, gravity, and the fundamental constants is complex, and changes in these constants could alter the timeline of cosmic evolution in unexpected ways. We might discover that the universe has been expanding for a different length of time than we currently believe. The cosmic microwave background radiation, the afterglow of the Big Bang, would carry signatures of any changes in fundamental constants during the early universe. This ancient light was released when the cosmos was only 380,000 years old, and atoms first formed as the universe cooled below the ionization temperature of hydrogen. If the speed of light or other constants were different at that time, the detailed patterns in this radiation would reflect those differences. Reanalysis of cosmic microwave background data with varying fundamental constants might reveal new information about the conditions in the early universe. The temperature fluctuations we observe today could have been shaped by physical processes operating under different fundamental constants, providing a window into how the cosmos evolved when the laws of physics themselves might have been different from what we observe today. The formation and evolution of the first stars and galaxies would have proceeded differently if fundamental constants were changing over time. Star formation depends critically on the balance between gravitational collapse and radiation pressure, a balance that is determined by fundamental constants, including the speed of light. If these constants were evolving, the first generation of stars might have been more or less massive than current models predict. The nuclear fusion processes that power stars also depend on fundamental constants through the strengths of electromagnetic and nuclear forces. Changes in these constants over cosmic time could have affected how efficiently stars burn their nuclear fuel, how long they live, and what elements they produce through nucleosynthesis. The chemical evolution of the universe might have followed a different path than we currently understand. Black hole physics would be profoundly affected by changes in fundamental constants. The event horizon of a black hole, the boundary beyond which nothing can escape, is defined by the distance where the escape velocity equals the speed of light. If the speed of light has been changing, the sizes of black holes and their interactions with surrounding matter would have evolved in ways not accounted for in current models. The information paradox, one of the deepest puzzles in theoretical physics, concerns what happens to information that falls into a black hole. This problem arises from the conflict between general relativity and quantum mechanics, and its resolution might depend on the precise values of fundamental constants. If these constants are changing, it could provide new insights into how information is preserved or destroyed in extreme gravitational environments. Gravitational wave astronomy would need to be reinterpreted if fundamental constants have been varying over time. These ripples in space-time travel at the speed of light and carry information about the cosmic events that produce them. If light speed was different when ancient gravitational waves were generated, the timing and characteristics of the signals we detect today would need to be reanalyzed to correctly understand their sources. The merger of two black holes or neutron stars releases gravitational waves that propagate across the universe at light speed. If this speed has been changing, the apparent timing of these mergers and the evolution of the binary systems that produce them would be different from current calculations. This could affect our understanding of stellar evolution, galactic dynamics, and the distribution of matter throughout the cosmos. Particle physics and quantum mechanics would face fundamental challenges if the speed of light varies over time. The standard model of particle physics treats the speed of light as a fixed parameter that determines the relationship between space and time coordinates. A varying light speed would require modifications to this successful theory, potentially revealing new physics beyond our current understanding. The uncertainty principle, which limits how precisely we can simultaneously know a particle's position and momentum, depends on fundamental constants, including the speed of light through Planck's constant. If these constants are changing, the fundamental limits of quantum measurement might themselves be evolving, with implications for our understanding of reality at the smallest scales. Quantum field theory, the mathematical framework that describes the behavior of subatomic particles, treats the speed of light as the fundamental parameter that connects space and time. Variations in light speed would require new formulations of quantum field theory that could account for changing fundamental parameters while preserving the essential insights about particle interactions and quantum phenomena. The cosmological constant problem, one of the greatest mysteries in modern physics, might find new solutions if fundamental constants are varying. This problem arises from the enormous discrepancy between theoretical predictions for the energy density of empty space and the observed acceleration of cosmic expansion. If fundamental constants are changing, the relationship between quantum vacuum energy and cosmic expansion might be different from current calculations. Dark energy, the mysterious force driving cosmic acceleration, might be intimately connected to varying fundamental constants. Some theoretical models propose that what we interpret as dark energy could actually be the effect of slowly changing speed of light or other constants. This would provide a more fundamental explanation for cosmic acceleration than hypothetical vacuum energy or exotic quantum fields. The fine-tuning problem, which questions why fundamental constants appear to be precisely set for the existence of complex structures and life, might find resolution through varying constants. If constants have been evolving over cosmic time, the apparent fine-tuning might reflect an evolutionary process rather than a remarkable coincidence. The universe might have gradually evolved toward configurations that allow increasing complexity. Cosmic inflation, the hypothetical period of exponential expansion in the first fraction of a second after the Big Bang, would need to be reconsidered if fundamental constants were changing. Inflation models depend critically on the assumed values of fundamental parameters, and changes in these constants could affect when inflation occurred, how long it lasted, and what observable consequences it produced. The multiverse hypothesis, which suggests that our universe is just one of countless others, with different fundamental constants, might be affected by the discovery of varying constants within our own cosmos. If constants can change over time within a single universe, this might reduce the need to invoke multiple universes to explain apparent fine-tuning, or it might suggest that the multiverse itself is more dynamic than previously imagined. Time itself might behave differently if the speed of light is changing. In Einstein's relativity, space and time are unified into space-time, with the speed of light serving as the conversion factor between spatial and temporal measurements. A varying light speed could mean that the fundamental nature of time is more complex than we have assumed, with implications for causality, simultaneity, and the arrow of time. The second law of thermodynamics, which describes the tendency of entropy to increase over time, might need modification if fundamental constants are changing. The relationship between energy, entropy, and time depends on these constants, and their variation could affect how isolated systems evolve toward thermal equilibrium and how information is preserved or destroyed in physical processes. Laboratory physics and technology would eventually be affected if fundamental constants continue to change at detectable rates. Atomic clocks, laser interferometers, and other precision instruments depend on the stability of fundamental constants for their operation. Long-term variations could gradually degrade the performance of these devices, or require constant recalibration to maintain accuracy. The global positioning system and other technologies that depend on precise timing would need to account for changing fundamental constants in their operation. If atomic transition frequencies are slowly drifting due to varying constants, the time standards that synchronize these systems would gradually become less accurate unless the effects are properly modeled and corrected. If light slows, what happens to time itself? Could the universe be older than we think, or does the slowing of light reveal that time and space are more intimately connected than we ever imagined, slowly evolving together as the cosmos ages and fundamental reality itself transforms? If the speed of light is gradually slowing down over cosmic time, the implications would extend far beyond abstract theoretical physics into the very practical realm of technology and space exploration. Every piece of modern technology that depends on precise timing, electromagnetic radiation, or quantum mechanics would be affected in subtle but potentially significant ways. From the global positioning satellites orbiting overhead to the fiber optic cables carrying internet data beneath our feet, a changing speed of light would touch nearly every aspect of our technological civilization. The global positioning system represents one of the most visible examples of technology that depends critically on the constancy of fundamental constants. GPS satellites orbit Earth at altitudes of approximately 20,000 kilometers, traveling at speeds of about 14,000 kilometers per hour. Each satellite carries multiple atomic clocks that must maintain synchronization to within a few nanoseconds to provide accurate position information to users on the ground. The GPS system already accounts for relativistic effects predicted by Einstein's theories. The satellite clocks run slightly fast compared to ground-based clocks due to the weaker gravitational field at orbital altitude, while they also run slightly slow due to their high orbital velocity. These competing effects result in a net gain of about 38 microseconds per day, which must be corrected for the system to maintain its advertised accuracy of a few meters. If fundamental constants were changing over time, these relativistic corrections would gradually become less accurate. The atomic clocks aboard GPS satellites depend on specific atomic transitions, whose frequencies are determined by fundamental constants, including the fine structure constant and the speed of light. Any drift in these constants would cause the satellite clocks to gradually fall out of synchronization with ground-based time standards. The accumulated error would be subtle at first, perhaps causing position measurements to drift by centimeters or meters over periods of months or years. However, as the effects compound over time, the GPS system could eventually become significantly less accurate or even unusable without constant recalibration. This would affect not only civilian navigation, but also military applications, scientific research, and the countless commercial activities that depend on precise positioning. Telecommunications technology would face similar challenges from changing fundamental constants. Fiber optic communications rely on precisely timed laser pulses traveling through glass cables at speeds determined by the speed of light and the refractive index of the optical fiber. If the speed of light were changing, the timing relationships that govern high-speed data transmission would gradually shift, potentially causing communication errors or requiring constant adjustment of transmission protocols. The wavelength division multiplexing used in modern optical communications depends on the precise frequencies of different colored laser light. These frequencies are ultimately determined by atomic transitions in the laser materials, which depend on fundamental constants. Changes in these constants could cause different communication channels to drift in frequency over time, leading to interference between channels or degraded signal quality. Radio astronomy would be profoundly affected by changing fundamental constants, as these observatories depend on extraordinarily precise timing to synthesize images from signals received by telescopes scattered across continents or even space. Very long baseline interferometry combines radio signals from telescopes separated by thousands of kilometers, requiring timing precision better than a few picoseconds to achieve the highest resolution images. If the speed of light or other fundamental constants were changing, the precise timing relationships that enable these measurements would gradually degrade. Radio astronomers might notice that their most precise observations become less reliable over time, or that systematic errors appear in their data that cannot be explained by instrumental effects or atmospheric variations. The Square Kilometre Array, a next-generation radio telescope currently under construction, will push timing precision to even greater extremes. This instrument will combine signals from thousands of individual antennas spread across multiple continents, requiring unprecedented stability in fundamental constants to achieve its scientific goals. Any variation in the speed of light could limit the telescope's performance or require new calibration techniques to maintain accuracy. Atomic clocks, the foundation of modern precision timekeeping, would be among the first technologies to show effects of changing fundamental constants. These devices work by counting oscillations of atoms transitioning between different energy levels, with the transition frequencies determined by quantum mechanics and fundamental constants. Different types of atomic clocks have different sensitivities to changes in these constants. If fundamental constants were changing, different atomic clocks would gradually drift apart in their timekeeping rates. Cesium clocks, which define the international standard for the second, are relatively insensitive to changes in the fine structure constant. However, optical atomic clocks, based on other elements like ytterbium or strontium, show much stronger dependence on fundamental constants and would drift more rapidly. This differential drift between different types of atomic clocks would eventually require redefinition of time standards or development of new calibration procedures. The International System of Time Coordination, which currently assumes that all properly functioning atomic clocks should agree indefinitely, would need to account for systematic drifts caused by evolving fundamental constants. Laser technology would face unique challenges from changing fundamental constants. The precise frequencies of laser light are determined by the atomic or molecular transitions that create the laser emission, and these transitions depend on fundamental constants through quantum mechanics. Changes in constants would cause laser frequencies to drift over time, affecting applications that depend on stable, precisely known wavelengths. Laser interferometry, used in applications ranging from gravitational wave detection to precision manufacturing, depends critically on the stability of laser wavelengths. The Laser Interferometer Gravitational Wave Observatory uses laser light with wavelengths stable to better than 1 part in 10 to the 21st power to detect the tiny space-time distortions caused by passing gravitational waves. If fundamental constants were changing, even these extraordinarily stable lasers would eventually show frequency drift that could be mistaken for gravitational wave signals or could mask genuine astrophysical events. The LIGO collaboration would need to develop new techniques for distinguishing between signals caused by gravitational waves and those caused by changing fundamental constants. Quantum technologies, including quantum computing and quantum cryptography, would face fundamental challenges from varying constants. These technologies depend on precise control and manipulation of quantum states, which are governed by the same fundamental constants that determine atomic transition frequencies. Changes in these constants could affect the coherence times of quantum states, the fidelity of quantum operations, and the security of quantum cryptographic protocols. Quantum computers use carefully controlled quantum systems to perform calculations that would be impossible on classical computers. The quantum gates that perform these calculations depend on precise timing and energy relationships determined by fundamental constants. If these constants were changing, quantum computers might require constant recalibration or might experience degraded performance over time. Semiconductor technology, the foundation of modern electronics, could be affected by changing fundamental constants through their influence on atomic and molecular properties. The band gaps that determine how electrons behave in semiconductors depend on quantum mechanical calculations involving fundamental constants. Changes in these constants could gradually alter the electrical properties of electronic devices. The effects would likely be too small to notice in most consumer electronics over human timescales, but precision instruments and scientific equipment might eventually show systematic drifts in their performance. Manufacturers might need to account for these effects in long-term product specifications or develop new calibration procedures for sensitive instruments. Space exploration would face new challenges if fundamental constants were changing over cosmic timescales. Spacecraft navigation depends on precise timing and communication with Earth using radio signals that travel at the speed of light. If this speed were changing, the time delays between Earth and distant spacecraft would not match theoretical predictions based on constant light speed. Missions to the outer planets already deal with communication delays of hours due to the vast distances involved. If the speed of light were different when these signals were transmitted compared to when they arrive, the actual travel times would not match calculations based on current fundamental constants. This could affect mission planning, spacecraft operations, and scientific data analysis. Future interstellar missions would be even more sensitive to changing fundamental constants. A probe traveling to Proxima Centauri, our nearest stellar neighbor, would require over 4 years for radio signals to reach Earth, even at current light speed. If the speed of light were changing over such timescales, mission controllers would need to account for these variations in their communication protocols and navigation calculations. The search for extraterrestrial intelligence would need to consider the possibility of changing fundamental constants when designing detection strategies and interpreting potential signals. If fundamental constants have been changing over cosmic time, the wavelengths and timing of artificial signals from distant civilizations might not match our expectations based on current physical constants. Precision manufacturing and metrology would gradually be affected by changing fundamental constants through their effects on the fundamental standards of measurement. The meter is currently defined as the distance light travels in a specific fraction of a second, while the second is defined by atomic transitions in cesium. If fundamental constants were changing, these definitions would need to be revised or supplemented with additional standards. Scientific instruments that depend on fundamental constants for their calibration would require new approaches to maintain their accuracy over extended periods. Spectrometers that measure wavelengths, frequency counters that measure oscillation rates, and many other instruments would need to account for systematic drifts caused by evolving constants. Medical technology could eventually be affected through the quantum mechanical processes that govern how radiation interacts with biological tissue. Medical imaging techniques like magnetic resonance imaging and positron emission tomography depend on precise understanding of atomic and nuclear processes governed by fundamental constants. Changes in these constants could gradually affect the accuracy of medical measurements or require new calibration procedures. The implications extend even to everyday technologies like computer displays and LED lighting, which depend on quantum mechanical processes in semiconductors and phosphors. While the effects would be imperceptible over human lifetimes, long-term changes in fundamental constants could gradually alter the colors and efficiencies of these devices. If the speed of light is slowing down, could our technology adapt? And could our journeys through the stars be altered in ways we have yet to imagine, as the fundamental constants that govern electromagnetic radiation and quantum mechanics slowly evolve, along with the expanding cosmos? As we stand at the threshold of a new era in physics and astronomy, the question of whether the speed of light is changing over cosmic time represents more than just an academic curiosity. It embodies our deepest quest to understand the fundamental nature of reality itself. The answer to this question will determine whether our current understanding of the universe rests on solid foundations, or whether we are on the verge of discoveries that will revolutionize our comprehension of space, time, and the laws that govern everything around us. The next generation of astronomical observatories promises to provide unprecedented precision in testing whether fundamental constants have remained stable throughout cosmic history. The James Webb Space Telescope, with its enormous mirror and advanced infrared instruments, can observe galaxies as they existed when the universe was only a few 100 million years old. These observations will extend our reach further back in cosmic time than ever before, potentially revealing evidence of changing constants during the universe's earliest epochs. The extremely large telescopes currently under construction will dwarf even the largest observatories operating today. The European Extremely Large Telescope, with its 39-meter primary mirror, will collect over 10 times more light than any existing ground-based telescope. This enormous light-gathering power will enable astronomers to obtain detailed spectra of distant quasars and galaxies with unprecedented precision, pushing the search for fundamental constant variation to new levels of sensitivity. The Square Kilometre Array Radio Telescope will revolutionize our ability to study the early universe through 21-centimeter observations of neutral hydrogen. This technique can probe cosmic epochs that are completely inaccessible to optical telescopes, including the period known as the Cosmic Dark Ages, when the first stars and galaxies were forming. Radio observations of the 21-centimeter line from this era could reveal whether fundamental constants were different during these crucial early phases of cosmic evolution. Gravitational wave astronomy is entering a golden age with increasingly sensitive detectors coming online around the world. Future gravitational wave observatories, including space-based missions like the Laser Interferometer Space Antenna, will be capable of detecting gravitational waves from sources across most of the observable universe. These measurements will provide completely independent tests of whether the speed of light has remained constant, as gravitational waves themselves travel at light speed. The precision of gravitational wave timing measurements will eventually become so extraordinary that they could detect fundamental constant variations that are too small to observe through any other technique. When two black holes or neutron stars spiral into each other billions of light years away, the gravitational waves they produce carry a record of the fundamental constants that existed when the waves were generated. By comparing these ancient waves with laboratory measurements, scientists may be able to trace the evolution of fundamental constants over cosmic time. Laboratory experiments will continue to push the boundaries of precision in fundamental constant measurements. New generations of atomic clocks based on nuclear transitions promise even greater stability than current atomic clocks. These nuclear clocks could be thousands of times more sensitive to certain types of fundamental constant variation, potentially detecting changes that are currently beyond experimental reach. Quantum sensing technologies are advancing rapidly, with new techniques for manipulating and measuring quantum states, enabling unprecedented precision in testing fundamental physics. Quantum entanglement, superposition, and other quantum phenomena can be harnessed to create sensors that approach the fundamental limits imposed by quantum mechanics itself. These quantum sensors may eventually detect fundamental constant variations that are too subtle for classical measurement techniques. The development of optical clocks based on trapped ions and neutral atoms continues to advance at a remarkable pace. These clocks are already approaching stability levels of 1 part in 10 to the 19th power, and future improvements may reach even greater precision. Networks of these ultra-precise clocks distributed around the world will be able to search for both temporal and spatial variations in fundamental constants with extraordinary sensitivity. Space-based fundamental physics missions offer unique advantages for testing constant variation. The microgravity environment of spacecraft eliminates many sources of systematic error that plague ground-based experiments, while the absence of atmosphere allows direct access to the full electromagnetic spectrum. Several space missions dedicated to testing fundamental physics are currently being planned by space agencies around the world. The Atomic Clock Ensemble in Space mission will test fundamental physics using multiple atomic clocks in orbit around Earth. By comparing different types of atomic clocks in the pristine environment of space, this mission will search for fundamental constant variations with sensitivity far exceeding what is possible on the ground. The results will either place the strongest constraints ever achieved on constant variation or potentially provide the first definitive evidence that constants are indeed changing. Artificial intelligence and machine learning are beginning to play increasingly important roles in the search for fundamental constant variation. The analysis of astronomical spectra from distant quasars generates enormous datasets that are difficult to analyze using traditional techniques. Machine learning algorithms can identify subtle patterns in these data that might indicate constant variation while rejecting the countless systematic effects that can mimic genuine signals. Deep learning neural networks trained on simulated spectra can recognize the signatures of fundamental constant variation with far greater sensitivity than human astronomers analyzing the same data by hand. These algorithms can process thousands of quasar spectra simultaneously, searching for correlated changes that might be too subtle to detect in individual objects, but become apparent when large samples are analyzed collectively. The integration of multiple observational techniques through sophisticated statistical analysis will provide the most powerful tests of fundamental constant stability. By combining results from atomic clock experiments, astronomical spectroscopy, gravitational wave timing, cosmic microwave background observations, and other approaches, scientists can search for correlated signals while rejecting systematic effects that would affect individual measurements differently. Bayesian statistical methods allow researchers to combine diverse types of evidence in a rigorous mathematical framework that accounts for the different uncertainties and systematic effects in each measurement technique. These approaches can extract weak signals from noisy data and provide robust estimates of the probability that fundamental constants are truly varying over time. The theoretical framework for understanding varying fundamental constants continues to evolve as physicists develop more sophisticated models that can make precise predictions for observational tests. String theory, loop quantum gravity, and other approaches to quantum gravity suggest specific mechanisms through which constants might vary, providing concrete targets for experimental searches. The connection between fundamental constant variation and other unsolved problems in cosmology, such as dark energy and dark matter, may provide new insights into these mysterious phenomena. Some theoretical models suggest that what we interpret as dark energy could actually be the effect of slowly varying fundamental constants, providing a more fundamental explanation for cosmic acceleration than exotic quantum fields or vacuum energy. If fundamental constants are indeed varying, this discovery would necessitate a complete revision of our understanding of the universe and our place within it. The apparent fine-tuning of physical constants that makes complex structures and life possible might reflect an evolutionary process rather than a remarkable coincidence. The universe might be gradually evolving toward configurations that allow increasing complexity and organization. The implications for the search for extraterrestrial intelligence would be profound if fundamental constants have been changing over cosmic time. Different regions of the universe might have experienced different evolutionary histories for their fundamental constants, leading to different possibilities for the emergence of complex chemistry and life. The galaxy might contain regions where the constants evolved in ways that favor or inhibit the development of technological civilizations. Future space missions to other star systems will need to account for the possibility of varying fundamental constants in their mission planning and scientific objectives. If constants have been changing over cosmic time, the physical conditions around other stars might be subtly different from what we observe in our local region of space. This could affect everything from planetary formation and stellar evolution to the chemistry of potentially habitable worlds. The development of new theoretical frameworks that can accommodate varying fundamental constants while preserving the essential insights of relativity and quantum mechanics represents one of the greatest challenges facing theoretical physics. These theories must explain why constants appear stable over human timescales, while allowing for variations over cosmic time, and they must make specific predictions that can be tested through observations and experiments. The unification of quantum mechanics and general relativity, the holy grail of theoretical physics, may require accepting that fundamental constants are not truly fundamental, but are instead emergent properties of a deeper underlying reality. If space and time themselves emerge from more fundamental quantum processes, the constants that govern physics in our familiar four-dimensional spacetime might be slowly evolving features of this emergence. The philosophical implications of varying fundamental constants extend far beyond science into questions about the nature of physical law, the meaning of mathematical constants, and the relationship between mind and cosmos. If the universe is not governed by eternal, unchanging laws, but by principles that themselves evolve over time, this would represent a fundamental shift in how we understand the relationship between mathematics and physical reality. Educational systems around the world will need to adapt to incorporate the possibility of varying fundamental constants into physics and astronomy curricula. Students will need to learn that even our most basic assumptions about the nature of reality might be subject to revision as our knowledge advances. This represents both a challenge and an opportunity to inspire the next generation of scientists to think deeply about the fundamental nature of the universe. The international scientific community continues to build the infrastructure needed to definitively answer whether fundamental constants are varying. This effort requires unprecedented coordination between different fields of science, from atomic physics and quantum optics to astronomy and cosmology. The question of varying constants has become a unifying theme that brings together diverse research communities in pursuit of a common goal. What would it take to definitively prove the speed of light is changing? The answer lies in the continued development of ever more precise experimental techniques, the construction of increasingly powerful telescopes and detectors, and the patient accumulation of data over decades or even centuries. The evidence must be overwhelming and come from multiple independent sources before the scientific community will accept such a revolutionary discovery. The future of cosmological research promises exciting developments, regardless of whether fundamental constants are truly varying. If constants are stable, this would confirm one of the deepest assumptions underlying modern physics and provide confidence that our theoretical framework is correct. If constants are varying, this would open entirely new avenues for understanding the universe and might provide keys to solving some of the greatest mysteries in cosmology. The search for answers is just beginning. As we look deeper into the universe with ever more powerful instruments and techniques, we may uncover truths that will forever change how we see light, time, and reality itself. As our journey through the mysteries of light and time draws to a close, we find ourselves standing at the edge of human knowledge, gazing into the vast unknown that stretches beyond our current understanding. The speed of light, that seemingly absolute constant that has served as the foundation of modern physics for over a century, may not be the unchanging pillar we once believed it to be. Instead, it might be just another feature of our evolving cosmos, slowly changing as the universe itself grows older and transforms around us. Throughout this exploration, we have seen how the simple question of whether light speed is constant touches every aspect of our understanding of reality. From the smallest quantum interactions within atoms to the grandest structures spanning billions of light years, the speed of light weaves through the fabric of existence like a golden thread connecting all phenomena. If that thread is slowly lengthening or shortening over cosmic time, it would require us to reweave our entire understanding of how the universe works. The evidence we have examined remains tantalizingly inconclusive. Ancient astronomical records hint at subtle discrepancies that might indicate changing constants. Distant quasar spectra show possible variations in fundamental parameters over billions of years. Laboratory experiments push the boundaries of precision, yet still cannot definitively detect the tiny changes that might be occurring over human timescales. Each measurement seems to whisper that something might be changing, but never quite loudly enough to overcome the noise of systematic uncertainties and experimental limitations. Perhaps this uncertainty itself tells us something profound about the nature of scientific discovery. The greatest advances in human understanding have often emerged not from definitive answers, but from the patient pursuit of increasingly precise questions. Galileo did not immediately prove that Earth orbits the Sun with his first telescopic observations, but he opened a window that eventually transformed our cosmic perspective. Darwin did not instantly demonstrate evolution through natural selection, but initiated a line of inquiry that revolutionized biology over generations of careful study. The search for varying fundamental constants may be following a similar path. Each new generation of experiments and observations brings us closer to an answer, whether that answer confirms the constancy of nature's laws or reveals that even our most basic assumptions about reality need revision. The journey itself has already transformed our understanding of precision measurement, quantum mechanics, cosmology, and the deep connections between different areas of physics. Consider the technological marvels that have emerged from this quest for ultimate precision. Atomic clocks so accurate they would lose less than a second over the age of the universe. Laser interferometers sensitive enough to detect distortions smaller than 1/10,000th the width of a proton. Telescopes capable of analyzing light that has traveled for over 12 billion years, carrying information about physical conditions in the early cosmos. These achievements represent humanity at its finest, pushing the boundaries of what is possible through ingenuity, persistence, and international collaboration. The philosophical implications of our investigation extend far beyond the technical details of experimental physics. If fundamental constants are indeed varying, it would suggest that the universe is not a static stage upon which physical processes play out, but rather a dynamic, evolving entity where even the laws of physics themselves participate in cosmic development. This would represent a profound shift from the mechanistic worldview that has dominated science for centuries toward a more organic understanding of cosmic evolution. The possibility that physical constants might vary also raises deep questions about the nature of mathematical truth and its relationship to physical reality. Mathematics has long been considered the language of nature, with its constants and equations expressing eternal truths about how the universe operates. If these mathematical relationships are themselves evolving over time, it might indicate that mathematics is not separate from nature, but is instead intimately embedded in the fabric of cosmic development. The apparent fine-tuning of fundamental constants for the existence of complex structures and life has puzzled scientists and philosophers for decades. If constants are varying over cosmic time, this fine-tuning might reflect an evolutionary process rather than an extraordinary coincidence. The universe might be gradually exploring different configurations of fundamental parameters, with complexity and organization emerging in regions where the constants evolve in particularly favorable ways. This perspective offers a new way of thinking about our place in the cosmic story. Rather than existing in a universe with arbitrarily chosen fundamental constants, we might inhabit a cosmos that has slowly evolved toward conditions that allow increasing complexity and the emergence of consciousness. Our existence would then be not just compatible with the laws of physics, but intimately connected to their evolutionary development over cosmic time. The international scientific community working on these questions represents humanity's collective effort to understand our deepest origins and ultimate destiny. Researchers from dozens of countries collaborate on experiments and observations that push the limits of human capability. They share data, techniques, and insights across cultural and national boundaries, united by the common goal of understanding how nature really works at its most fundamental level. Young scientists entering this field today will spend their careers developing even more precise techniques and building upon the foundations established by previous generations. Some may discover definitive evidence that fundamental constants are indeed varying, revolutionizing our understanding of physics and cosmology. Others may prove that constants are truly constant, confirming the stability of our current theoretical framework. Either discovery would represent a monumental achievement in human understanding. The tools of the future promise even greater precision in probing the constancy of fundamental constants. Quantum sensors that harness the strange properties of superposition and entanglement to achieve measurement sensitivities approaching fundamental quantum limits. Space-based observatories free from the distortions of Earth's atmosphere. Artificial intelligence systems capable of finding subtle patterns in vast datasets that would escape human detection. These advances will continue to push the boundaries of what questions we can ask and answer about the nature of reality. As we contemplate these future possibilities, we are reminded that the scientific enterprise is fundamentally about expanding the horizons of human knowledge and capability. Each generation builds upon the achievements of those who came before, asking deeper questions and developing more sophisticated tools for finding answers. The question of whether fundamental constants vary represents one of the deepest inquiries humans have ever undertaken, touching the very foundations of physical reality. The beauty of this scientific quest lies not only in its ultimate destination, but in the journey itself. Every precise measurement, every theoretical insight, every technological advance contributes to our growing understanding of how the universe works. Even if we never definitively answer whether the speed of light is changing, the pursuit of that answer will continue to drive innovations that benefit all of humanity. The speed of light may be the ultimate limit, but what if it is not as unchanging as we believe? As we journey through space and time, we continue to push the boundaries of our understanding, always searching for the next great discovery. The universe holds its secrets carefully, revealing them only to those who ask the right questions with sufficient precision and patience. Rest now, beneath the stars, knowing that the mysteries of the universe await. The ancient light that reaches your eyes tonight has traveled across vast distances and enormous spans of time, carrying within it the secrets of cosmic evolution and the fundamental nature of reality itself. Whether that light traveled at constant speed or varied subtly during its journey remains one of the great open questions of our time. The night sky above you is not just a beautiful display of distant lights, but a laboratory where the deepest questions about existence play out across cosmic scales. Each photon that enters your eye has potentially witnessed the slow evolution of fundamental constants over billions of years. The twinkling starlight connects you to the grand cosmic story that began with the Big Bang and continues to unfold around us every moment. As you drift off to sleep under this canopy of ancient light, remember that you are part of a species that dares to ask whether even the most fundamental aspects of reality might be subject to change. You live in an age when humans can measure time to precision beyond imagination, detect gravitational waves from colliding black holes, and peer back to within a few 100 million years of the universe's beginning. Tomorrow will bring new observations, new experiments, and new insights into the deepest mysteries of existence. Scientists around the world will continue their patient work, making measurements of unprecedented precision and developing theories of ever greater sophistication. The question of whether fundamental constants are varying will gradually yield to this persistent inquiry, revealing another piece of the cosmic puzzle. The universe is vast, ancient, and full of wonders we are only beginning to comprehend. The speed of light, whether constant or varying, is just one thread in the magnificent tapestry of existence that connects quantum mechanics to cosmology, laboratory experiments to astronomical observations, and human curiosity to the deepest truths about reality. Rest peacefully in the knowledge that this great adventure of discovery continues, carrying us ever closer to understanding our place in the cosmos.